Okay, hello, these are the answers for test 1. Starting with question 1 here. A double-slit experiment uses light of wavelength 650 nanometers. The slits are separated by 0.08 millimeters, and the interference pattern is observed on a screen 3 meters away. A particular bright fringe is found to be 4.88 centimeters from the central maximum. Determine the order M of this bright fringe. So for this double slit, we are going to use the slit spacing formula, or I guess the fringe spacing formula for double slits. And we're looking for the order M, so I'm going to rearrange this. M equals xd over lambda L. And plugging in. Now, I am choosing to put everything into meters. No other reason than that I think it is easiest for me personally to convert this way. If you find it easiest to convert to a different unit, please do that. After plugging everything in, should get about m equals 2. So for centimeters, I have times 10 to the negative 2 to convert to meters. For millimeters, I have times 10 to the negative 3 to convert to meters. And for nanometers, times 10 to the negative 9. The 3 is already in meters, so I can leave that be. Our answer for number 1 was 2. For number 2, monochromatic light of wavelength 300 nanometers falls on a slit. The angle between the two third-order bright fringes, that will be important, that are on opposite sides, again important, of the central maximum is 24 degrees. Estimate the slit width. Great, so now this time we have single slit. And we are looking for slit width. So let's rearrange. Great. So now we are ready to try and plug some stuff in. First off, M. What is M? We're not told the order directly, what number it is, so we need to go find that out. However, what we are told is that the angle between the two third-order bright fringes. So we are looking at the third-order fringe. Now, that does not necessarily mean that m is equal to 3 in this case. But we are also told that these are bright fringes. In other words, these are maxima. So let's go take a quick look at our formula sheet here. Now, this is the old one, the messy formula sheet. There is a nicer version out there now. But you will want to identify this formula here, the same formula we've used. And as you can see, we have two different possible lists for m, for minima and maxima. We just determined that we are looking at maxima, so we are going to be using, well, m maxima, that string with fractions, odd numbers divided by 2. So we are also told that this is the third order, so we're going to go ahead and pick the third item in this list. So that is the plus or minus 7 over 2. As we discussed in class, we're just going to be using the positive values for this. So we're going to take positive 7 over 2 for m. Great. So we have 7 over 2 for m. Our wavelength is just 300 nanometers. And again, I always like to convert everything to just base meters, so I'm doing that again here. Lastly, sine. This is not just 24 degrees. This is actually 12 degrees. That was a little sloppy. 12 degrees. This is because if this here is our central maximum, this here will be our 24 degrees. However, the formula works off just half here, which is 12 degrees. So we only need half the angle because that's how the formula was created, how it's intended to be used. So our final D value here, after you plug everything in, is going to be 5.05 times 10 to the negative 6 meters. There we go. Number 3, 3 ideal polarizing sheets are arranged in parallel planes. The second sheet has its transmission axis oriented at 40 degrees relative to the first sheet. The third sheet has its transmission axis oriented 90 degrees relative to the first sheet again. So really quickly, let's do 90 minus 40 degrees to give us 50 degrees relative to second. Missing an O in there somewhere. Second sheet. All right, what percentage of the unpolarized light is incident on the first polarizer? And then what percentage of the original light intensity emerges from the third polarizer? Okay, so the intensity passing through the first polarizer is going to be exactly half of the original light intensity here. This is because the original light hitting the first polarizer is unpolarized. So half of it goes through. For the second one, we take that amount of light that made it through the first one and multiply it by the cosine squared of the angle between them to get this ugly decimal that I decided to work with for no particular reason other than to just make things harder for myself, I guess. And so that is the amount of light that makes it through the second polarizer. Now for the third, we take that amount of light that makes it through the second polarizer, and we multiply it by the cosine squared of the 50 degree angle we already found between them. And plugging all that in, you get about 0.1212 I naught. Taking this number here, multiply it by 100%, and you get 12.12% transmission of the original light intensity passing through the third filter. So that was questions 1, 2, and 3. Question 4. Unpolarized light that is traveling through alexandrite and is incident on a layer of water at an angle of 37.23 degrees. The index of refraction for alexandrite and water are 1.75 and 1.33 respectively. Determine if the reflected light is fully or partially polarized. So this is a Brewster angle question. Here's our formula for it. Now going ahead and rearranging, we get the arctangent or the inverse tangent of n2 divided by n1. And plugging in, we're told that it is traveling through alexandrite and incident on water, so therefore we know water is n2 and alexandrite is n1. Plugging this in, we get 37.23 degrees, so therefore it is fully polarized. Great. Number 5, what is the energy of a photon from the CMBR, or cosmic microwave background radiation, with wavelength of 1.95 millimeters? Provide your answer in electron volts. Now, first I'm going to start with the equation for the energy of a photon. So here we are. And instead of plugging in HC and converting to, as they are, and converting to electron volts later, instead I'm going to use this helpful little constant, where Planck's constant times the speed of light is equal to 1,240 electron volt nanometers. Going to use this, going to be very helpful. Now what this does mean is I cannot just use 1.95 millimeters. I need to convert this to nanometers. So now both of my nanometers cancel out. I'm left with just electron volts. And I'm left with some small little decimal. Or, as many of you put your answers, in microelectron volts. Totally fine. So either one there was accepted. Number 6, brass has a work function of 4.7 electron volts. Part A, what is the wavelength of the lowest energy photon that will cause brass to emit electrons? Okay, so I'm going to do A, B, C, each in their own colors so that they are very distinct. And I will start with my work function equation here. Because I'm given work function and I'm asked about wavelength. So I'm going to go ahead and rearrange these here. So wavelength equals hc over the work function, hc over 4.7. Now, I am doing this one without using my handy little constant from the question before, just to show anybody who does prefer to do it this way a good example. So here I have taken my 4.7 electron volts in the denominator and multiplied by our little converting factor here to convert that to joules. Because remember, regular Planck's constant, which I'm actually going to go ahead and replace these with. So 6.626 times 10 to the negative 34. Remember that the units for this are in joule seconds. So we do have to convert either the 4.7 to joules or Planck's constant to electron volts, one or the other. So that was the answer for part A here. Part B, sorry, was the stopping voltage if light of 200 nanometers is used instead. Okay, so I'm going to go ahead and use my kinetic energy formula, or you might hear me refer to it as the stopping voltage formula. Basically the same thing, but kind of. So for now, we're going to solve for this kinetic energy of the highest energy electrons that will be emitted. Here we get hc over the 200 nanometers minus the 4.7 work function. And in this case, just to keep the pattern going, I guess, I'll use my 1240 constant again. I guess in this case, just to show how much more convenient it can be. So our stopping voltage, after plugging everything in, is just 1.5 electron volts. Or sorry, that's the kinetic energy. Our stopping voltage for these electrons is 1.5 volts. Seems like a small difference, but it does matter. Lastly, for C. Light of 500 nanometers is shone on the brass surface. Explain why no electrons are emitted. Now, you can go ahead and do the calculation, and you can see that EK is negative if you go ahead and calculate it. So therefore, electrons do not have enough energy to be emitted. So the wavelength of light, 500 nanometers, is just too long of a wavelength and too low energy to actually emit electrons from the surface of brass. It's 500 nanometer light just isn't energetic enough. We need a minimum of 264 nanometer light that we calculated in part A. So 500 is longer than that. 264 was the minimum. That was the longest possible. So, doesn't work. Moving on. These were the lab-related concept questions. Now, these were done extremely well overall. So I don't think I'm going to spend too much time explaining my answers here or writing out good full sentence answers. Instead, I think I'm just going to be doing some point form notes as answers because everybody just did so incredibly well on this section. Anyway, let's jump into it. List one specific error source from any lab that is not human error. If you need an idea for this, please ask me. And plenty of you did come ask me. That was great. Thank you. I will go ahead and use the example or one similar to the one that I gave you guys who asked me. In a lab, you may have had to measure a specific distance. So, measuring a distance L, right? So measuring a distance L. What if this was accidentally done on a diagonal? Or, so I will say measuring tape was sagging, leading to a longer measurement, or I'll say a longer L. So for part A, explain why this causes some error. Well, measuring a distance L, using a measuring tape, the measuring tape was sagging, leading to a larger distance L than what the real value should be. So that's why this causes some error. B, explain how exactly this impacts your result. Too big or too small, a final value. Now, this one did depend on the lab. So many different answers for this. What I was really just looking for was a logical breakdown of how this would affect your later calculations. So let's take a look. I'll bring up some equations in my answer here to support my answer from a previous lab. So in this case, it causes theta equals the inverse tangent of r over L to be too small. And then a small theta causes 1 over the sine of theta to be too big in the overall result. So what I was really looking for here was really just a logical follow through of the steps of how exactly the measurement being too big could impact the final value that we were calculating. So I followed it through. L in this lab that I'm referencing here was used twice in 2 different calculations. Technically, L itself was used in one calculation, which then the result from that was used in another following calculation, so it impacted twice. If you really want to say 3 times with the final calculation being some percent error, go ahead. I'm not too worried about that though, because we're talking about what could cause that percent error. So I don't really know if I'm going to count that one. I'm not going to, not right now at least. what I was really looking for part B was just a logical breakdown of how it could impact your results specifically, not just you saying it could be too big or too small. I wanted a very specific answer. For part C, explain how to fix or account for this error in future labs. In this case, we used a measuring tape that was sagging, leading to a longer L. So in this case, you could support the measuring tape so that it no longer sags. Just something super simple, super quick to explain how to fix the lab. You could have replaced this with a different measuring tool or measuring method. Doesn't matter, as long as it was a reasonable solution. So that was for number 7. I should also mention that it goes without saying that the answers for all the lab-related concept questions are up to interpretation. You might have answered it differently, but still gotten a completely correct answer. There are multiple correct answers for these questions, for most of them at least. You'll see in later on, some of these questions do have distinct answers, but something like number 7, more open-ended. So, 8. In a double slit diffraction experiment, the spacing between the slits is slowly increased. In the beginning of the experiment, there's a clear double slit pattern, and at the end, there is only a clear single slit pattern. Explain why this happens when the spacing between slits is increased. So I got a bit of a 2-part answer here. First one is spacing becomes so large it acts as 2 separate single slits instead of a double slit. So as the spacing increases, the width of the beam hitting both slits can only cover a single slit instead of both as well. That is my second answer here. So it's kind of the same answer all in one. Some of you rolled this into a single paragraph. Some of you broke it down into 2 separate points. Great, didn't matter. But so the laser beam is too narrow to illuminate the widely spaced slits at the same time. So even if the slits were still closely spaced enough together to get some meaningful interference pattern for double slit interference, the laser wouldn't be wide enough to cover both slits anyway. So it couldn't illuminate both of them anyway. So potentially 2 answers here, depending on the specific setup. So those are the answers for 7 and 8. For 9. Below is an example of a diffraction pattern created by a below is an example of a diffraction pattern created by a diffraction grating created using a blue laser. I'm sorry, I should have worded that differently. That is terrible. If I ever do this question again, that will be fixed. I'm sorry, I didn't realize how terrible that was until just now. The blue laser is swapped out for a green laser. In the space below the diagram, draw in 5 new dots where you think the green laser diffraction pattern will appear. Now, there's no distinct locations for where these might be. No, actually, I got an idea that might make this look quite nice. Oh, no, undo. Okay, never mind. Did not work. Okay, so we're still going to have this single dot in the center. That's not going to move. That one stays where it is. And the green dots will be more spaced out than the blue dots. Doesn't matter exactly where you draw them, as long as the green dots are more spaced out than the blue ones. So if I draw some dashed lines on the blue ones, you can see clearly that the green ones are more spaced out. That's really all I was looking for here. Nothing too amazing. So in this one, explain why the green pattern is different from the blue pattern. Use the diffraction pattern equation below to support your explanation. Now, we used this equation specifically because it was for diffraction grading. That is the pattern we are looking for here. We are also told it's created using a diffraction grading. So that's where this formula is coming from. And so I'll color code this, why not? Green has a longer wavelength than blue. So lambda for green is going to be greater than lambda for blue. Therefore, angular spread theta will be larger for green light, making the pattern more spread out. And there we go. Now, some people tried to answer this using double slit interference with X spacing being with this formula here. Now, while your reasoning was correct, it didn't quite make sense with how you were explaining it. I spoke to you in person about this, and we went over it and talked about the differences there. But so just know that formula not to be used for this. It is a diffraction grading question. So that was question 9. 10. I believe this was the last one. Yes. Now, I thought this question was going to be a bit more difficult, so I broke it down into parts A, B, C, and D, and then everybody aced the thing. So I should have left it in its original, more difficult form instead of giving you these extra parts A, B, C, and D to break it down and lead you towards the correct answer. I should have left it. But oh well. Anyway, here we go. Monochromatic... Oh, let me move that back. There we go. Monochromatic light passes through a narrow vertical slit and produces a diffraction pattern on a distant screen. Part A, describe the orientation of the diffraction pattern produced by the stationary vertical slit. The pattern is horizontal. Awesome. Part B, if the slit is rotated by 90 degrees, how does the diffraction pattern change? Well, pattern is rotated by 90 degrees. Great. I hope the brightness changing all the time isn't affecting the video. Oh well. We'll see. Part C. Now imagine that the slit is rotated rapidly about its center during the exposure so that it completes many full rotations while the pattern is being observed. If the slit continues rotating through all possible angles, what happens to the overall appearance of the diffraction pattern? 2 points. A bit of a hint here. Will it look like a different diffraction pattern you have seen before? Yes, because it is spinning, it will look like a pattern from a circular aperture. It will look like a diffraction pattern from a circular aperture. So the overall appearance of the diffraction pattern will begin to look like a diffraction pattern from a circular aperture. Part D, explain why the pattern in Part C has that specific shape while the slit is spinning. So the spinning slit approximates a circular aperture about its axis of rotation. It is never obstructed in this one circular space, producing a circular pattern. Now, I'll try to draw a quick little diagram of this. So if we have, and actually, maybe I can get it to create me some rectangles that are at least a little bit identical to each other. And let's create just one more here. Sure. Okay, so here's our slit that is spinning. And you can see, if I zoom in nice and close here in the center, we have what appears to be a circle. So as the slit spins through all infinite angles, we will get a better and better and better approximation of a circle here. Now, yes, some light, sorry, cat hair on the screen, had to blow it off. As the slit spins, yes, of course, light is still going to pass through the slit. However, it will be constantly passing through the circular to create a circular aperture. And theoretically, the horizontal pattern or the vertical pattern or the diagonal pattern from the slit at any given time as it's spinning should line up with parts of the circular pattern that's being created anyway. So that was it for the test. Overall, extremely well done. I made this way too easy, so expect the next one to be a bit harder. Sorry, I guess. I don't know whether to apologize for that or not. Anyway, thank you for listening. If you have questions, please email me or ask me in class. Bye-bye.